this looks very promising. So looks like this whole wiring mess that we produced here with all the multiplexers does the right thing. We can shift input values to the left and to the right. We're shifting in the appropriate carry bit that we're selecting with the carry operation multiplexer here. We can also just do a regular pass through, in which case nothing happens, and we can pass in a 0 even where the left hand side is just set to a constant 0. And if we're doing a shift, we're presenting the shifted out bit to the carry flag up here, such that we actually have a place to store it for future use. And if we're not doing a shift, if we're passing the value through or we're injecting a 0, we're just using the carry output of the adder and present that to the carry flags register. So that should allow us to do the regular add and add with carry that we had before, but now we also have the option to do the left and right shifts with the appropriate interaction with the carry flags. So the only thing left to do is to bring the CPU back in and hook this ALU back up to all the control signals that it has. Let me do that. All right, I brought the CPU back out. This is how I left it when I removed the ALU. And let me bring the updated ALU, which we've changed today, back into the picture. Looks good. The ALU is getting bigger, which is a good sign. I think it will grow by one more breadboard eventually, but not today. And so all that's left to do is to hook all the control and data signals of the ALU back up to the CPU and then give it a try and see if it works. First up, let me hook up power and ground. We have a lot of loose connections that we should make. I'm really looking forward to the day when we put some of these components onto a proper backplane, which has a proper power distribution network, because that's going to be a good point also to hook up all these loose breadboards that we're currently developing and basically get a better power supply story going. But for the time being, these loose wires is just what we'll have to deal with. So I think that's all the power connections made. Let's move on to maybe the left-hand side, which is where we've been doing some work today. This wire here is the read data port 1 of the register file, which produces the left-hand side that we need to feed into the ALU. But it no longer goes directly to the adder. We now connect it to the input of the shift unit of the ALU. It's getting more difficult to make these connections because we have so much logic all over the place here. Then the other wire here is read data port 2 of the register file. This produces the right-hand side input into the ALU. So we'll have to connect this up to the right-hand side. Next up, we have this wire here. This is the ALU result wire that goes to the ALU buffer, which then drives it onto the right data port if we want to store the ALU result into the register file. So this needs to hook up to the output of the ALU. Then we have the clock signal of the flags register. This we have to hook up to the rest of the clock signals. And then we have the clock enable input of the flags register here, which we've been hooking up to the ALU buffer's output enable down here. And we're just going to do the same thing again. Then there's this connection here. This is pin 12 and 13 of the instruction. This we've been using to drive the carry operation control signal. So let me hook that back up. And as of today, we also have this shift operation control signal on the left-hand side here that we need to hook up to the rest of the CPU. And I think for the time being, we're going to do the same thing as we did for the carry operation. And we're just going to bring these two bits over to the instruction itself. And we're going to hook up bits 14 and 15 of the instruction to the shift operation, such that whenever we do an ALU operation, bits 12, 13 pick the carry operation and 14, 15 pick the shift operation. And then we'll do something more fancy with it once we have proper instruction decoding and ALU operation decoding. And I think that's it. That's all the data lines connected and all the control lines wired up. So let's actually try to make use of this new shift capability we have in the ALU. Let's go and update the instruction set architecture of the CPU to make use of these new control lines here. Update the assembler, and then let's see if we can write an interesting program that uses this new functionality. All right, so we have this new shift operation in the ALU, which is connected to bits 14 and 15 of our instructions. So first up, let's go update the instructions at architecture document to reflect what these bits do. So the last time we hooked up bits 12 and 13 to the carry operation. Now let's do the same thing for the shift operation. When the shift operation is 0, we're setting the left-hand side input of the adder to 0. And we're just forwarding whatever we select with the carry operation to the adder's carry input. And we're taking whatever the carry output of the adder is, and we're presenting it to the carry flag as the next carry bit. When the shift operation is 1, we're just forwarding whatever the value is that comes out of the register file without doing a left or a right shift. And same as above, we're just forwarding the carry we select with the carry operation to the adder, and then we take whatever the carry output is that comes out of the adder, and we're presenting this to the carry flag register to be stored. Now to the interesting part. When the carry operation is 2, we're doing a left shift. We're taking whatever comes out of the register file, we're shifting that left. And then at the bottom, we're shifting in whatever the carry input is that we selected with the carry operation bits. And because we're already using the carry input during the shifting, we're setting the adder's carry input to a 0. And left shifting the value that comes out of the register file will make the topmost bit, bit number 7 of that value, pop out of the number. And we're taking that value that pops out of the number and we're presenting it to the carry flag register to be stored there, such that subsequent instructions can make use of whatever we shifted out. So the carry output of the ALU, which is whatever we're presenting to the carry flag register to be stored, is going to be bit number 7 of the value that comes from the register file, which is the bit that got shifted out by the left shift. And when the shift operation is 3, we're doing a right shift. We're taking whatever comes out of the register file, shifting it by right by 1 position, and we're using whatever the carry operation selects as a carry input, and we're shifting that in at the top. And again, since we're using the carry input for the shift, we're setting the adder's carry input to 0. And because the right shift will make the lowest bit of the value that comes from the register file pop out of the number, we're taking that lowest bit, bit number 0, and we're presenting it as the ALU's carry output, such that it gets stored in the carry flag register, where the next instruction can make use of it. Let me clean this up a bit. Let me do the same thing for the carry operation up here. Instead of just saying it's an add or a subtract, let me actually clearly state what is going on in hardware. When the carry operation is 0, the carry operation multiplexer produces a 0 as the carry input into the ALU. And on top of picking what the carry input should be, we're also using this carry operation bit to decide whether we want to invert the right-hand side or not. And if it's an even number, we're just feeding whatever comes out of the register file through to the right-hand side input of the adder without inversion. When the carry operation is 1, we're producing a constant 1 as the carry input. And because it's an odd number, we're inverting whatever comes out of the register file before we feed it into the adder's right-hand side. And for carry operation 2 and 3, we're setting the carry input to whatever's currently in the carry flag register. And again, when the operation is even, we're just passing through the value that comes out of the register file as the right-hand side. And when it's odd, we're inverting the right-hand side that comes out of the register file before we feed it into the adder. Alright, pretty cool. So those are the 4 control bits that the ALU has at the moment, 2 for the carry operation, 2 for the shift operation. And by combining the 2, we can make all kinds of cool instructions. Let me scroll down to the instructions and let's see what we can do with this. First up, we need to update the add and subtract instructions. They currently have bits 14 and 15 set to 0, but since bits 14 and 15 now control the shift operation, we have to set them to the value 1 to select shift operation 1, which is just passing through the left-hand side coming from the register file unchanged without doing any left or right shift and without setting it to a constant 0. This now changes the encoding, and this should allow the add and subtract instructions to continue working. One nice thing we can do now that we have this shift operation, and by setting it to a 0, we can basically forcefully inject a 0 as the left-hand side to the adder, is we can have a negate instruction, which takes a source operand from the register file, negates it by basically doing a subtraction but setting the left-hand side to the constant 0, and then storing the result into some destination register. So by picking shift operation 0, we're forcefully setting the left-hand side that we feed into the adder to a 0. And by setting the carry operation to a 1, we're doing a subtraction, and we're basically taking that 0 on the left-hand side and we're subtracting whatever comes in as the right-hand side. And then we're storing the result into the destination register. And since this shift operation here, if we set it to 2 or 3, allows us to do left and right shifts, let's actually define a few operations that make use of this mode. We should now be able to take a value from the register file, shift it 1 position to the left, and shift in a 0 at the bottom. So let's call this shift left logical, and we'll just have one operand. Basically, we're reading the value in RD, doing the left shift, and then restoring back to RD. Now, let's think about how we can encode this. First up, it's an ALU operation. So the lowest 4 bits need to be a 4, as is the case with all the other ALU operations. Then we have a destination register, but now we'll keep the source register at a 0, and with a pull down register in the actual CPU, when we select a 0 as the source register, we're actually going to produce a 0 value as the right hand side input to the adder. And by doing so, the adder will not perform any operation. The right hand side is set to 0, and if we're careful to set the carry input of the adder to 0, the adder will just be a no operation, and it will basically forward whatever comes in from the left hand side to its output. So we're going to read this destination register from the register file that will be presented as the left hand side input. The carry operation is set to 2, which is going to do a left shift. We're selecting carry operation 0, which is going to produce a 0 carry input. So the left shift will shift in a 0 at the bottom. And then this will just flow through the adder because the source operand, the right hand side is 0, and the carry input to the adder is also 0. And the result will be stored back to register RD. And on top of that, by selecting left shift as the shift operation, we're also presenting the topmost bit of whatever came in from the register file as the left hand side input as the new carry flag, such that the bit that pops out of the number when we do the left shift gets stored in the carry flag. We can do a similar thing, but instead of doing a logical shift, we can do a shift with carry, where instead of shifting in a 0 at the bottom, we shift in the current state of the carry flag register. We're still going to do a left shift, which is going to shift in this carry input signal. And this time we can set the carry operation to 2, which is going to set that carry input signal to whatever is currently in the carry flag register. And as you can see, by carefully setting the carry operation, we can pick what bit gets shifted in at the bottom of a left shift, which is pretty sweet. And we can do the exact same thing, but in the other direction. We can have a shift right logical and a shift right with carry. And now, instead of setting the shift operation to a 2, we set the shift operation to a 3, which is a right shift. This is going to take whatever comes out of the register file, shift it 1 position to the right, shift in the carry input that gets selected with the carry operation as the topmost bit, and it will present the lowest bit of what comes from the register file. This is the bit that gets shifted out by the right shift as the carry output of the ALU to be stored in the carry flag register. Let me update the encoding here as well. Cool, that's a few useful new instructions. We can negate the number without reading what's actually in the destination register first. And we can do 4 different flavors of shifts, 2 left shifts, 2 right shifts, in a logical flavor where we shift in a 0 at the top or bottom, or a carry flavor where we shift in the current carry flag register value at the top or bottom. And both of them will store whatever bit gets shifted out of the number in the carry flag, such that we can use it in subsequent instructions. Okay, so with these new instructions defined, let's go look at the assembler and let's go teach the assembler about these new instructions that we might want to use. We have this test.s file that we've been using to test the assembler. Let me add the new instructions there. So right here we've been testing the ALU operations. Let me add the new instructions right here below that. We have this new negation instruction and then the shifts. Cool, let's run this file through the assembler and let's see what breaks. And as expected, the assembler doesn't know about the negate instruction, so let's go change that. For the change, let's start out at the opcodes and define the new opcodes that we need. We've added the negate instruction, and we've added the shift instructions. And then we need to be able to parse them. So right here we're parsing the add and the subtract and add with carry. Let me add a line for the negation. Then after all the ALU operations, let me add the shifts. First up, shift left logical, but this time we only need the destination register, we don't have a source register. Let's do the same thing for the shift left with carry, and the exact same thing for the right shifts. And as you can see, there's a lot of repetition here, and not a lot changes between the registers. So at some point we'll refactor the assembler a bit to make this a bit more streamlined. So this is parsing. We also want to be able to print the instructions back out when the user requests that. And again, before the add, let me insert the negation. And then after all the ALU operations, let's add the new shifts. First, the shift left logical. And again, it only has one register operand. Then we're going to do the same thing for the shift left with carry. And let's do the exact same thing for the right shifts. So that's the opcodes, the parsing and the printing. That leaves the actual encoding of the instructions. Let's start with the negation here before the add. The lowest 4 bits are unchanged, the hex value 4. Then we encode the two operands as before. But since we've now added this shift operation to the ALU and we're using bits 14 and 15 of the instruction to control those, starting at bit number 12, we actually now have 4 bits that control how the ALU operates. And if we go consult the instructions at architecture document, for negation, these topmost bits, 12, 13, 14, and 15, need to be set to the value 1. And since we've changed the encoding for add and subtract in the instruction set architecture, we also have to change the encoding here in the assembler. So again, we're now using 4 bits to encode the ALU operation. And if we go check back in the instruction set architecture document, for add and subtract in their two flavors, we have to set the topmost bits to a 0, 1, such that the left-hand side gets passed through unchanged. Alright, so that's add with carry, and subtract with carry updated. Let's specify the encoding for the new shift operations. Let's start with shift left logical. The lower 4 bits stay unchanged, the hex value 4. Then we encode register operand RD. There is no register operand RS, so we're going to remove that. That will leave those bits as a 0. And then if we check the instruction set architecture document, for the shift left logical, we have to set the topmost 4 bits to the value 1000. Let's do the shift left with carry. For shift left with carry, the topmost 4 bits have to be set to 1010. And then let's do the right shifts. And if we check the instructions at architecture document, the right shifts have the topmost 2 bits set to a 11. Alright, that should be all the necessary assembler changes. Let's see if we can assemble that test file. And indeed, that seems to work, no errors or warnings. If I scroll up a bit, you can see the new instructions encoded here. Negation has the 1 at the top, and then the shifts have the 8, A, C, and E, as we've had them in the instructions at architecture, and the source register is set to a 0. And then up here for add and subtract, we have changed the encoding of the topmost 4 bits. Okay, with this all working, let's go write a new program. Let's maybe call it testshift.s. And as per usual, let's clear the registers to 0 to get started. I'm going to steal that from the previous program that we wrote. So at this point, we have all the registers cleared to 0. First up, to start out, let's maybe try the new negate instruction. Let's just load 3 numbers into a few registers, and then let's negate them in place and see if the correct value comes out. Let me quickly write up the binary pattern that we expect to see here. So at this point, registers are 0, 1, and 2 should contain the values -1, -10, and -100. Let me add a knob here to separate this from the next part of the program. Next up, let's maybe try to do left shifts. And to test the shift left logical and the shift left with carry, so the kind of shifting through the carry bit operations, let's do a 16-bit left shift. First up, let's clear registers R2 and R1. And then let me load an interesting value into R0. This value is going to make it easy to see the shifting that we're actually doing. Let's start out by doing a shift left logical on register R0. And what we expect to happen here is for R0 to be shifted to the left by 1 bit. And because it's a logical shift, we're going to shift in a 0 at the bottom. But as you can see, because we did a left shift, this topmost 1 bit popped out of the number and got lost. But it actually didn't get lost, it gets stored in the carry flag. So on top of observing a left shift in register R0, we should also see the carry flag be set to a 1. And now we have the topmost bit that we shifted out stored in the carry flag register. And so now we can do a shift left with carry on, for example, register R1. This will take this carry flag and shift it in at the bottom of the register R1. Before this instruction, the register contains the all 0 value. So the register is 0, so we're shifting that 0 to the left and we're shifting in the carry flag. And as a result, we would expect to see that carry flag appear in the bottommost bit of register R1. And since we did a left shift and we shifted out a 0 topmost bit, that gets now stored in the carry flag. Let's do the exact same thing again. This time we're shifting out the 0 at the top, which gets stored in the carry flag. And then when we get to the shift left with carry, we're shifting that 0 in at the bottom. Let's do this again. We shift out that 1 at the top, that gets stored in the carry flag. And because it's shift left logical, we're shifting in a constant 0 at the bottom. And then when we do the shift left with carry, we're shifting in that 1 from the carry flag register. Let's do this one more time. Again, we're shifting out a 1, gets stored in the carry flag, and we're shifting in a constant 0 at the bottom because this is a logical shift. And then when we do the shift left with carry, we're shifting in the 1 from the carry flag register. And if you look at the value in R0 and R1 together, you can actually see that we shifted the value to the left, and all the bits that shifted out of register R0 got shifted into register R1. So this is in effect a 16-bit left shift. That's very cool. Let me add an up here as a separator. And then let's actually do the exact same thing backwards. Let's do a 16-bit right shift through the carry flag. And let's see if we can shift the numbers as they are right now back into the original position. So first up, we're going to do a shift right logical. This time, because we're doing a right shift, we have to shift register R1, the upper 8 bits first. At this point, R1 contains the value 0, 0, 0, 0, 1, 0, 1, 1. So we're taking the value in R1 and we're right shifting it. The bottommost bit is a 1. This gets shifted out and stored in the carry flag. And because it's a logical shift, we're shifting in a 0 at the top. And now for the bottom 8 bits, we're going to do a shift right with carry, which is going to take that bit that popped out of the upper 8 bits and it's going to shift that in at the top. So we take the value of our 0 at that point, we shift in the carry flag at the top, and the bit at the bottom pops out and gets stored in the carry flag. Let's do this another time. We're doing a shift right logical on our 1, so we're shifting in a 0 at the top. The 1 that gets shifted out of the number gets stored in the carry flag. And then we're doing a shift right with carry on our 0, so the carry flag gets shifted in at the top, and the 0 that pops out at the bottom gets stored in the carry flag. Let's do this again. Shift in the 0 at the top in R1. The 0 that we shift out at the bottom gets stored in the carry flag. When we do the shift right with carry on R0, we're shifting in that carry flag at the top. And again, the 0 we're shifting out at the bottom gets stored in the carry flag. And one more time. Shift in the 0 at the top of R1. The 1 we shift out gets stored in the carry flag. And when we do the shift right with carry at register R0, we shift in that carry flag. And the 0 that pops out at the bottom gets stored in the carry flag register. And at this point, we're back to where we started. Alright, so that's the shift left logical and carry, and the shift right logical and carry tested out to do a 16-bit shift. Let me add a knob as a separator at the bottom here. Now let's see what other interesting things we can do with this shifting through the carry flag. One of the cool things we should be able to do is to bit reverse a number, basically by shifting the bits out of the number in one direction and storing it in the carry, and then shifting it into another number in the other direction. We should be able to reverse the bits in the number. So let's give that a try. First up, let me load some value into register R0. That should make it easy for us to see if the reverse actually worked. And now to do the bit reversal, we want to shift the bits in this number out in one direction and then shift it into another register in another direction. But I want to have the value in R0 stay unchanged, so we have something to compare against. So let me copy R0 into some other register, which is going to be the register that we actually modify and we shift the bits out of. To get started, let's shift the first bit out of the value in register R2. Let's use a right shift for that. So shift right logical on R2. This is going to take the value in R2, shift in a constant 0 at the top because it's a logical shift, which makes the bottommost bit pop out of this number, and this gets stored in the carry flag. And now we have that bottommost bit in R2 in the carry flag, and we can use a shift left with carry on R1 to basically shift that carry flag back in R1 is all 0 at this point, so basically we're just shifting the carry flag in at the bottom. And because we shifted out a 0 value, the carry flag gets set back to 0. So let's see what happens if we do this again. We're right shifting R2, so we're shifting in a 0 at the top, and the one at the bottom gets stored in the carry flag. And then we're doing a left shift with carry on R1, which means that carry gets shifted in at the bottom, and we're shifting out a 0 at the top. Let's do this again. We're shifting in a 0 at the top of R2. The one that pops out goes into the carry flag, and then we shift the carry flag into R1. One more time. Shift in a 0 at the top of R2. The one that we shift out goes into the carry flag, and that gets shifted into register R1. And now at this point you can see a pattern emerge. The lower bits of R1 are actually the reversed version of the lower bits that we had in R0. So as we continue this pattern, these bits will wander further to the left, and we'll see the bottom bits fill in with the remainder of R2. So let's see if that works. Let me just step through it pretty quickly. And so shifting bits out of a register in one direction into the carry flag, and then shifting the carry flag back into another register in the other direction, if we do that 8 times, we can bit reverse the 8 bits in a number in one of our registers. And this can be handy for certain algorithms in practice. For example, the butterfly operation in the fast Fourier transform, you can implement pretty efficiently if you're able to shuffle the bits in an index number around, which isn't all too different from what we're doing here for the bit reversal. Another thing that comes up pretty often in certain kinds of algorithms is population count, basically looking at the number and counting the number of 1 bits that it has. So let's see if we can implement that. Let me add a knob separator first, and then let's see if we can implement Popcount. Let me clear the registers back to 0. R2 is already 0 because we shifted all the bits out, but R1 and R0 contain some numbers, so let me override those with a 0. To get started, let's load the number that we want to run the population count on into register R0. I'm just going to pick a few random bits here. So these are 4 1s and 4 0s. So the result of the popcount operation should be 4 because there's 4 1s in this number. Again, as we did before, let's keep the number around in R0 unchanged so we have something to compare against. And let me copy it into register R2 such that we have a scratch register that we can actually shift things around in and destroy the number. And now we're going to do a similar thing as with bit reversal. We're going to shift bits out of register R2 and into the carry flag one by one. And now we don't want to shift the carry flag into another number, but we want to take the carry flag and add it to a counter where we count how many of the bits that we shifted out were a 1. And let's say register R1 is going to be our pop count result, the number of 1s that we've seen. And it's currently 0, which is good because we haven't seen any bits yet. And we can use an add with carry to take the carry flag and add it to the value in register R1. Register R6 contains the value 0, so it doesn't really contribute anything to the addition. So whenever the carry flag is set, we're basically incrementing the counter in R1. And whenever the carry flag is not set, we're leaving R1 as it is. So this is a perfect way to tally up bits as we shift them out of the number R2. Let me quickly take note of the bit patterns in the register such that it's going to be easier to follow along when we run this. Alright, so that's the first bit shifted out and tallied up. Let's do this again, which will do it for the second bit. This time we're shifting out a 0. So the carry flag will be a 0, which means that the add with carry will not change the value in R1. Let's do this another time, which is going to handle the third bit. We're shifting out another 0. So nothing will change in our pop count. Do it for bit number 4. This time we shifted out a 1 again, which is going to cause the pop count to count up by 1. So after shifting out the first 4 bits of the number, the pop count will be 2, because we shifted out 2 1s in the process and tallied them up in register R1. Let's do this some more. Bit number 5, shift out a 0 again, add with carry remains unchanged. Bit number 6 is a 1, so the carry is 1, which means that the add with carry is going to increment the value in R1. Once more for the 7th bit, this is another 1, so add with carry will increment R1 again to the value 4. And again for the final 8th bit, which is a 0, so the carry flag is 0, and thus add with carry is not going to change the value in R1. And at this point, the register R1 corresponds to the pop count of register R0. And if we take a look, that checks out. There are 4 1s in the input number, and we get a 4 as a result in register R1. And all we had to do is basically do the exact same thing 8 times over, shift 1 bit out of the number, and then decide what to do with that bit, which is now in the carry flag. And in this case, we use the add with carry to tally the bits up into a counter. Let's do this again for a different number, maybe one that is a bit more interesting, that has more ones, and let's use a right shift for a change. I'm going to pick a random new number. This one has 7 ones, so we want the pop count to read as 7 at the end. I'm loading this into register R2 such that we don't destroy the old number in R0 and the old pop count in R1, just so we have something to look at when we actually execute this on the CPU. And then same as we did above, let me copy this number into a scratch register that we can actually change and destroy the value in through our shifts, but we still have the original number around. And then let's do pop count again, but this time let's do a shift right logical. And at the end here, once we've done this shifting and tallying up 8 times, the register R3 contains the pop count of the value in register R2. And since the value in R2 has 7 ones and only 1 0, the pop count ends up being 7, as we would expect. And now way back when we started to build up the CPU and the register file and the program counter, we used the registers to display this kind of bit ping-ponging pattern where a single bit just shifted to the left and all the way back to the right. And now that we have actual shift operations, we can display this pattern a lot more efficiently with a dedicated operation. So let me do that. Let me add a knob separator first and then clear the register file back out to 0. And then let me load register R0 with just a 1, which is going to set the lowest bit. And that's going to be the bit we're going to shift all the way to the left and then back all the way to the right. Okay, at this point the lowest bit is set in register R0. And let's first use a bunch of left shifts to move that bit all the way to the left. And after 7 left shifts, the bit has shifted all the way to the left. Let me add a knob afterwards. And then let's do the same thing again, but with right shifts and shift the bit all the way to the right again. And after 7 right shifts, we're back to where we started from, where the lowest bit is set in register R0. And now all that's left to do, I think, is to jump backwards and do this left and right shifting in a loop. These are 15 instructions, and every instruction is 2 bytes, so we want to do a jump relative with immediate, and we want to jump backwards by 30 bytes in program memory. Now, at some point in the future, we'll extend the assembler to support labels such that we can just type down a label at the beginning of the loop and then jump to that point. But we don't have that yet, so we have to do a little bit of arithmetic and compute the byte offsets manually, which is error prone, but it works for these simple programs. All right, I think that's it. We have a few pretty interesting uses of left and right shifts. All the way at the top, we are clearing the registers to 0 as always. Then we're making use of this new negate operation, just to give that a test, not really related to shifts. Then we do a 16-bit left shift, a 16-bit right shift. We're doing a bit reversal of a number. We're doing pop count, once with a left shift and once with a right shift. And then we have this ping-ponging bit pattern loop here that is just going to make a single bit shift all the way to the left and to the right again in the register. So let's assemble this program. Let me run through the assembler. Let's see what the assembler thinks. That looks pretty good. I think this might be the longest program we've written so far. Let me scroll all the way up. Clearing registers, the negation operations, left shifts, right shifts in 16-bit. We do a bit reversal, pop count with left shifts, pop count with right shifts. And here is our ping-ponging loop. And at the end, you can see there's a jump relative with immediate, the one that jumps back and closes the loop. And we jump back to the hex address C4. And indeed, C4 is the first shift instruction that's going to shift the whole thing back to the left again. So this is going to do a left shift and the right shift, and then go back up, do the left shift and the right shift until we turn the processor off. Sweet, let me call make and create the binary file for us. Now let me get the program flash memory out of the CPU build. I'm going to put it into the programmer, and then all that's left to do is to actually write this binary into that memory. And that's it. Let me put the memory back into the CPU, and then let's power it up and step through the program and see whether it works. Let me step it out of reset. First up, we're going to clear the register file as per usual. So the first instruction loads a 0 into register R0. And then we're going to move the 0 value all the way through the register file. Next up is a knob to separate it from the next part of the program. Let me step over that. And now we're in the first interesting part of the program. First up, we're going to try the new negate instruction. To do that, we'll load the numbers 1, 10, and 100 into registers R0, R1, and R2. That's 1, 10, and 100. And now we're going to negate each of the numbers. The first instruction is a negate R0, R0, which means we're going to read the value in R0, negate it, and then store it back into register R0. On the ALU over here, you can see that the carry operation is set to 1, which is a regular subtract. So we're subtracting the right-hand side from the left-hand side. But the shift operation is set to a 0, which is the 0 operation, which injects a 0 on the left-hand side of the adder. And as you can see, the register file on the read data port 1, which feeds the left-hand side, actually produces the value 1, which is what we're selecting from register R0. But the 1 doesn't make it all the way through to the adder because the shift operation, which controls how the left-hand side input is being changed, is set to 0 and basically ignores anything that comes in from the register file and just sets the left-hand side to a 0. And this is how we get a negate operation. We fix the left-hand side to a 0 and then we subtract whatever comes in through the right-hand side. And as you can see, the result here is a -1. And so if I hit the clock, register R0 gets set to -1. Then we're going to do the same thing for register R1. We're reading the 10 from the register on both read data port 1 and read data port 2. We're bringing them over to the ALU. The shift operation is set to 0, so the first one, the left-hand side, is ignored and is set to a constant 0. And then we're subtracting the right-hand side from that. And as a result, we get the value -10. And if I hit the clock, -10 gets stored into register R1. And then the same thing for 100. If I hit the clock, we see -100 appear in the register file. Cool, that looks like it's working. In the future, we might want to change the negate instruction such that it takes only one register operand and it basically reads that, negates it, and writes it back to that same register. Next up is a knob to separate it from the next part of the program. And now we're doing a 16-bit left shift through the carry flag. This is a convenient way for us to test the new shift left instructions, the shift left logical and the shift left with carry. First up, we're clearing the registers R2 and R1. And then we're loading a more interesting pattern into register R0. And now we're treating registers R0 and R1 as a 16-bit value, and we're trying to do a left shift of that 16-bit value, which means we're shifting the register R0 value to the left, which makes the topmost bit drop out of the register, which is going to get stored in the carry flag, and then we're doing a left shift on the second register, but this time with a carry, and that's going to shift in whatever bit popped out of the first register at the bottom here. And overall, this will have the effect of just left shifting the entire 16-bit value. So first up, we're doing a shift left logical of the value in register R0. And as you can see on the ALU here, the shift operation is set to a shift left. And because it's a shift left logical, we have the carry operation set to a 0, which means produce a constant 0 value for the carry. So when we're doing the left shift, as you can see here on the left-hand side input to the adder, this is the result of the left shift. We're shifting the bits of the left-hand side input number to the left. And then at the bottom, we're shifting in a 0, which is basically the carry that was selected through the carry operation here. The topmost value of register R0 is a 1, and by left shifting the value, that 1 drops out of the 8 bits that we can represent. And as you can see here, that 1 that we shifted out is now being presented to the carry flag register to be stored such that the next instruction can make use of it. And so when I hit the clock, we should see the register R0 value shift one step to the left, and the carry flag register update to a 1, which is basically capturing the topmost bit that got shifted out. And that works. The value shifted to the left, and we now have a 1 in the carry flag register. Next up, we're doing a shift left with carry on register R1, which is the upper 8 bits of our 16-bit value. And as you can see, the register has the value 0, so shifting isn't going to be all too interesting. But looking at the ALU, we can see that the shift operation is still set to a left shift, which makes sense, we're left shifting. But the carry operation is now set to 2, which instead of using a 0 value as the carry, uses the current value in the carry flag register as the carry. And so when I hit the clock, you should see the register R1 update to the all zeros value shifted over by 1 place and the current carry flag being shifted in at the bottom. And that's exactly what happens. And so overall, this had the effect of shifting the entire 16-bit value 1 step to the left, and we used the carry flag as kind of an intermediary to hold this bit that we would lose through the shift. Now we're going to do this a few more times. First up, we're just going to left shift the value in R0, which works. And because the topmost bit was a 0, nothing lands in the carry flag register. Then we're doing a left shift with carry on R1, which is going to shift the value in R1 to the left and shift in the current carry flag. But the current carry flag is a 0, and as a result, you can see that we're just shifting in a 0 at the bottom here of the left-hand side. So when I hit the clock, the value just shifts over, and the 0 that we shifted out of the lower 8 bits gets shifted into the upper 8 bits. Then we're going to do it one more time, which again makes us shift the value in R0 1 step to the left, which makes a 1 pop out of the register, which gets stored in the carry flag register, which we then shift in with the shift left with carry in register R1. Let's do one more. Shift this 1 step to the left. That made a 1 pop out at the top, which is now in the carry flag register. And now we're going to do a shift left with carry, which is going to shift the value in R1 to the left, and it's going to shift in that 1 from the carry flag register. And as a result, if you concatenate the value in R1 and R0, overall, this is a 16-bit value that is just the old 16-bit value that we had at the beginning, but shifted left 4 times. Let's try to do the same thing in reverse. We have this 16-bit number here, and we should be able to do 4 right shifts, again, regular ones and the ones through the carry, and we should get back the original number. First, let me step over the knob we had inserted as a separator. And now we're doing the right shifts. So shift right logical, as you can see over here at the ALU, the shift operation is set to 3, which is the shift right, and the carry operation is set to 0, which is a regular add, which basically picks a 0 as the carry input. So as you can see here, we're taking the current value in register R1, we're shifting it right by 1 space, which means we're shifting out the lowest bit here, and that lowest bit we're presenting to the carry flag register again to be stored as the carry flag. And so when I hit the clock, we should see this number shift 1 step to the right, and that lowest bit here should appear here in the carry flag register. And that works. Perfect. Next up, we're doing a shift right with carry on register R0. And basically, we're going to take the value in R0 and we're going to shift it right by 1 position. And then over here at the ALU, we're still selecting shift operation 3, which is the right shift. But now again, with the carry operation set to 2, which is the add with carry, which makes the carry multiplexer here pick the current value in the carry flag as the carry instead of a constant 0. And that's the value that's getting shifted in as the top bit when we do the right shift. And so when I hit the clock, you should see the value in R0 shift 1 step to the right. And at the top, you should see the current carry flag register being shifted in. And that worked. Perfect. Now we're doing this a few more times. Shift right logical again, which is going to shift the value in R1 1 step to the right, which you can see happen here, and the value that pops out at the bottom gets presented to the carry flag register. And so when I hit the clock, that value in R1 shifts to the right, and the bit we're losing gets stored in the carry flag register. And then we're doing a shift right with carry on register R0, which makes R0 shift 1 step to the left and shift in this carry flag value at the top, which also works. Now the right shift on R1. The carry flag is 0 because there was a 0 bit at the bottom. Now we're doing a shift right with carry, which is going to shift register R0 to the right, and we're going to shift in a 0 value at the top because the carry was a 0. And we're doing it once more, shift R1 to the right, which moves that bit that dropped out into the carry flag register. And when we do the shift left with carry on R0, R0 is going to shift to the right, and the current state of the carry flag register appears as the top bit. And as you can see, we're back to the beginning. Register R1 is back to the all zeros value, and register R0 is back to this initial pattern we had. So with shift left and shift left with carry, we were able to shift 16-bit values to the left. And with shift right logical and shift right with carry, we were able to shift 16-bit values to the right. So that's pretty exciting. Another good use of the carry flag register here, allowing us to perform arithmetic on wider values than what the native registers of the processor actually support. Let me step over the knob we have here as a separator. And now we're going to use the shifts and the carry flag to reverse the bits in a number. First up, we're loading a new immediate value into register R0. And now we're going to take the value in R0 and bit reverse it into register R1. So at the end, we want to see register R1 be the exact reverse of register R0. First up, we're going to copy the value from R0 into R2 such that we have a place for us to modify that value, and R0 will stay as it is such that we can compare it against the new value afterwards. Our strategy is to right shift the value in R2, which makes the lowest bit pop out and be stored in the carry flag register, and then do a left shift on register R1, which makes the bits in R1 shift one step to the left and the current carry flag appear at the bottom. And if we do this 8 times, we should have shifted out every single bit in register R2 into the carry flag and then back in to register R1. But because we're using a right shift to shift them out from R2 and the left shift to shift them into R1, the bit pattern should reverse. So let's see if that works. First up, we want to see the value in R2 shift one step to the right and that lowest bit appear here at the carry flag register, which works. Pretty cool. And now we're doing a left shift with carry on register R1, which should shift the carry flag register in at the bottom. And that worked. Now we're going to do the same thing. Shift one bit out of R2 into the carry flag, and then left shift in the carry flag bit into register R1, which also worked. Same thing again. Shift a bit out of R2 and shift it into R1. Next up is a 0 bit, so we're shifting a 0 value out of R2. Now we're left shifting that into R1. And as you can see, that 0 got shifted into R1. Again, right shift a bit out of R2 and shift it into R1. Again, right shift the 0 out of R2 and shift the 0 into R1. And again, right shift a bit out of R2 and left shift it into R1. And now this has only been 7 times, so we need to do it one more time. Right shift a bit out of R2, which is going to be a 0, and then left shift that bit into R1, which is going to add a 0. And that looks pretty promising. Register R1 is the exact bit reverse of register R0. So that worked like a charm. Let me step over the knob separator. Next up, we're doing a pop count. This is basically counting the number of 1 bits in a register. First up, we're going to clear the 2 registers that we've used. And now we're loading a new value into register R0. And now we're going to count the number of 1 bits in this value. And again, as we did before, we're going to copy the value from R0 into R2 such that we have a place where we can shift things around, and we still keep a copy of the original value for us to compare. And so now to do the pop count, we're going to shift a bit out of the register R2. We're doing a left shift, so the topmost bit is going to land in the carry flag register. And now we're using an add with carry to basically take the value in R1, add the register R6, which is a constant 0. But because it's an add with carry, we're also considering the value in the carry flag register. And because the carry flag is the bit that we shifted out of the number before, we're basically adding a 0 to R1 for every 0 bit we shift out, and we're adding a 1 for every 1 bit we're shifting out. And so since we shifted out a 1 before, if I hit the clock, register R1 is going to count up to 1. We're going to left shift another bit out of R2. It's a 0 this time. So the carry flag stays at 0. And what happens when we do the add with carry now is we're taking the 1 in register R0 and we're basically just adding a 0, so nothing changes. And we're going to store the 1 back unchanged into register R1. Left shift the next bit out of register R2, which is another 0, so we're going to add another 0 to register R1, which makes it stay at 1. That's getting interesting again. We're left shifting another bit out of R2, which is a 1 bit, which makes the carry flag 1. And now we're doing another add with carry, and this time, because the carry flag is set, we're actually adding a 1 to register R1. Now we're shifting out another bit from R2. It's another 0, so R1 is not going to change. But the next bit is a 1, so when we shift that out of register R2, we're going to add a 1 into R1. Next bit we're shifting out is another 1, which appears in the carry flag, and again that makes us add a 1 to register R1. And now the final 8 shift, we already have no more bits in register R2, so we're shifting out a 0, which lands in the carry flag as a 0, and when we add with carry this into R1, nothing changes. But as a result now, we loaded a value into R0 which had 4 1s and 4 zeros. And because we shifted out each of the bits individually and then used the add with carry to basically tally them up in register R1, we're now left with the value 4 in register R1, which is indeed the pop count, the number of ones in that original value. Let's try a different number a bit more quickly this time. So we're loading R2 with a new value. Then we're going to do the same thing again as we did before. We're going to copy R2 into R4 such that we can leave R2 untouched. And then we're doing the same thing again, but this time we're using right shifts, because technically it doesn't matter if we shift the bits out to the left or to the right, as long as we basically somehow shift all the individual bits in the number through the carry flag at some point. So we're using right shifts now. We're shifting out a 1 and adding that to our count, another 1 and another 1, which makes the count go up to 3 as you expect. Next one is a 0, which doesn't change the count. And then we have 4 more 1s to shift out. So that makes our count go to 4, 5, 6, and 7. And those were 8 shifts and 8 add with carries, so we considered all the bits in our 8-bit registers. And the pop count is now 7, which indeed is the number of 1 bits in that value that we loaded into register R2. This is very exciting. We have a way to count the number of bits that are set in a register, which is a surprisingly common operation for a certain kind of algorithm. Let me step over the knob separator. And now we're going to clear the registers 3, 2, and 1. And we're going to set register R0 to a 1. And now as a final demonstration in this program, we're going to take this 1 bit and shift it all the way to the left and then back all the way to the right. And then we're going to loop around and just do this forever. First, we're going to do 7 shift lefts. Pretty cool. That made the bit go all the way to the left. Then we have a knob as a separator. And then we're going to do 7 shift rights, which should make the bit walk all the way back to the bottom. Perfect. And then to close the loop, we have a jump relative with immediate, and we're jumping back 30 bytes in the program, which is basically the beginning where we started left shifting. And there you go. As you can see, we're back at the beginning of the loop. We're back to doing left shifts. And I can now hit run and basically let the clock loose, and we should see this 1 bit just walk back and forth in the pattern that we had all the way back when we started to do loads into the register file. Very cool, that's working. And I can even increase the speed, which should make this pattern move a bit more quickly. That's very cool, that seems to be working. And it's fun to see that the processor is at least capable of a little bit of speed, even though there's a lot of these like loose power connections, which on the breadboards is usually a death sentence to anything that resembles speed. But as soon as we start to move things more onto PCBs and actual a backplane, which has a proper power connection, we'll be able to run the CPU at a fairly decent speed. At some point, we'll also look into what the critical paths are in the CPU and how we can engineer it such that it runs at a decent clip. So I'm super excited about this. My CPU can now shift the bits in a number around, which is very useful. We've added these multiplexers here to the ALU, which basically sit between the left-hand side input of the ALU itself and the left-hand side input of the adder. And these multiplexers give us a chance to take the left-hand side value that comes out of the register file and set it to all zeros, which is useful in its own right, or use it unchanged, or shift it left by one position, or shift it right by one position. And we've used this new capability to add a shift left logical and a shift left with carry, which is similar to add with carry interacts with the carry flag, and also a shift right logical and the shift right with carry, which allows us to shift bits to the right through the carry flag. And on top of it all, since we now have the ability to set the left-hand side input of the adder to 0, we were able to introduce a negate instruction, which takes the right-hand side and negates it, turns it into its negative version, and then stores that into a different register. And so that shows how these control signals here, one for the carry operation and one for the shift, are really useful to be combined into all kinds of interesting instructions. And as we move forward with the ALU and we add more of these control lines, we'll get more knobs we can turn to actually do interesting operations on the ALU. And we can tie it all together by taking a few of these control inputs and then assigning an instruction label to them. And this will allow us to do the shifts and the adds we already do, but also the XOR operations, comparisons, and all kinds of interesting things. In the future, I'm pretty sure we'll have a fancier shift unit that can shift by any number of bits, not just one step to the left or right. But being able to shift by just one position is kind of the basic starting point that allows our CPU to do a lot more complicated things and do a lot more interesting computations. It's great to see that the ALU is already pretty powerful, and it allows us to do a few interesting things like a pop count or a bit reversal or these wide shifts. But we're now starting to run out of instruction bits. We've used the top 4 bits of the instruction already to pick what we want to do with the carry and to pick how we want to shift the left-hand side input of the ALU. But in the future, we also want our ALU to be able to do logic operations, comparisons, and some other things. So we're going to need a lot more bits, probably another 4 or 5. And we definitely don't have the instruction bits available to feed them up. In the next video, I think I want to come up with a form of ALU operation decoding. Basically a bit of logic that takes the top 4 bits, say, from the instruction and converts them into the actual control signals at the ALU. Because not all combinations of control signal values are going to be actually useful instructions in the ALU. Right now we have 9 instructions that use the ALU. We have add, subtract, left and right shift, both with and without the carry, so that's 8, plus the negate, which is 9. But we're using 4 bits from the instruction to control that. And those 4 bits would give us 16 different operations, but we're actually only using 9 of them because the others might be useless or might be weird instructions that we don't really have a use for. And as you can imagine, if we add another 4 or 5 bits here, we might have 256 or 512 different combinations of the control signals, but I'm pretty sure there aren't 512 different ALU operations that are actually meaningful that you could do on an 8-bit CPU. So by introducing some form of operation decoding, we'll be able to take, say, the top 4 bits of the instruction, which gives us 16 different possibilities, and produce the correct combination of control signals for each of those combinations. And I'm pretty sure that 16 is roughly the number of useful operations that we can do on this ALU. And then if we need more, we might want to add another bit, so we have 32 operations available. But as a result, we'll only use, say, 4 bits from the instruction to drive all these control signals. And so this decoding in the ALU will help us to not directly expose all the control signals to the instructions, but to have a kind of abstraction in between where the ALU supports a few distinct operations, which all have their own opcode number, a 4-bit number. And that's the 4-bit number we can write into the instruction. And then the ALU will do the decoding on its own to actually figure out how it wants to set its 8, 9 control signals, however many we'll have. This operation decoding in the ALU will allow us to do a lot more complicated stuff in the ALU with just a limited number of instruction bits we have available. So I really can't wait to finally get that done. That's something for the next time though. Thanks a lot for watching. Like and subscribe if you want to see more of this, and see you next time.